Finish off the design patterns, then take a break, and then move on to next set of lectures. We'll be doing version control for a lecture and a half or so. Let me remind you, so we haven't finished design patterns because we kind of spent some time last lecture with that shell shock bug, which I thought was time well spent. But that kind of put us in a position to leave for today's lecture a very important design pattern, which I definitely want to teach. It would have been nice to kind of teach it with the rest of design patterns. Let me remind you the structure of the last lecture on design patterns. I introduced the concept of design patterns, and then we went over 4 design patterns. For each one, I introduced the problem to be solved, and then I sometimes discussed the naive solution, and then I presented the design pattern for that problem. And this was all done in the context of this simple application. So it's an editor. It's a GUI editor that has characters that can be put together into lines, columns, pages, and that makes a whole document. And we've looked at the composition design patterns, which tells us, suggests a way to organize these data structures. Decorators, this was used to add borders and scroll bars and any combinations of thereof. What else did we use? We used the bridge pattern and the factory pattern. So I think those were the 4 patterns that we looked at last time. And I left for last a pattern that has to do with iterating over various elements of the document. So the problem, the prototypical problem that I'm trying to address here is some sort of traversal of the document in search for something or to do some transformation. I'll use spell checking here, but you can think search and replace, counting lines, counting pages, counting images, things like that. Okay, so spell checking, as an example, requires traversing the document, and you will need to see every glyph on every page, on every line, and so on. And this is typical of many traversals. Okay, what would be one way to organize, to write the code for spell checking? Let me actually, before you answer that question, and also kind of help bring back to your memory the structure of the document. It's important to think how we're going to organize the data structure. So we have a document object that has a list of page objects, right? 1 to at least 1. And then the page has columns, I think. The columns have lines. And the line has essentially the glyph. Some of them could be character glyphs, other could be drawings or pictures. Okay? So it's a tree structure. And you're doing spell checking. How would you write the code? There's many good answers at this stage. Yes?
Question, is spell checking involve grammar?
No, just search for words in a dictionary.
Is it spell checking or is it word searching? Like, are we looking to correct words that are misspelled or just looking like searching for a specific occurrence?
Doesn't matter for the purpose of this. I could have said counting words. That.
We iterate through the glyphs in a line, and then when we encounter a space glyph, then we know that's like a word, and then like we look up that word in the dictionary, and then like if it's not there.
Okay, good. So I'm really thinking maybe spell checking confused you because I didn't mean to make it complicated for how you actually look it up in the dictionary, how you correct it. It's just the searching, the iteration part, which was the beginning of how you started. So he said we iterate through the glyphs and then find spaces to essentially find the words. Well, it's not quite so simple because the glyphs are the leaves of this tree, right? You have glyphs on many lines, on many pages, on many. So to even iterate through the glyphs, you have to iterate through the pages. For each page, you have to iterate to the columns. Then you have to iterate to the lines. And then for each line, you iterate to the glyphs. And there's also the case when the word kind of spreads to lines, which may actually spread to columns, which may spread to pages. Because a word could start on one page and then hyphenated, ends on the second page. But you can do this, exactly following this recipe. You just have to write all of the code that does all of this recursive traversal and be careful about, when a word has started on one part of the tree and continues on the other part of the tree. All right? Because if you draw this out, it looks like a tree like this. And the actual letters are the leaves. If you could iterate through the leaves without bothering the structure on top, would be great. Because you would see exactly all the letters in sequence, no matter what page, what columns they are in. So now I'm going to ask you to abstract a little bit the solution, because, as I said, we're going to have several such features in our product. Not just even counting words, the word count. It's going to need a very similar traversal. When you have several things that need to do the same kind of thing, you're trying to think of a structure that abstracts away the commonality from the specific parts. So now think of how you're going to organize this traversal such that all traversals share some code, and then there's some differences between them, like spell checking, looking up in the dictionary is different than counting words and such. These are things that I suspect you've done or used before. Maybe haven't programmed before. Is the question clear? If not, ask me to clarify.
Wait, what's the question?
Instead of writing one monolithic traversal of this whole thing, finding the spaces, considering all the cases when the words start on different pages, and then repeating that, copy and pasting all that stuff for the counting words and for find and replace, I want you to think how to organize that code such that they have the common part is the same between all of those traversals, and only the difference is separated. I want to share all that commonality. I think that you were the first.
You can create like a spell checking method, and if it's not like a word, you just pass it to the.
You can create a spell checking method in each glyph. Who would implement this traversal? Going through all the pages, all of the lines.
Do like dot spell check, and then it's gonna tell this page is this spell check, and the pages.
Okay. So each of these glyphs, including the intermediate ones, is going to have a dot spell check, and it's going to call this dot spell check. And if I want to count words, well, that's exactly what I don't want. I don't, because the dot spell check and dot count words here is going to look identical. For the purpose of a page, it looks identical. I don't want to have this code duplication. I want to share.
We could look at this and see that we need like a new glyph isn't sufficient for our purposes of trying to find occurrences of words, so we could create a new word object, like somewhat in the local hierarchy.
Okay, what you're saying is to create a word object. That is actually quite tricky, because where do you put that object? Because it may span 2 lines, 2 columns, 2 pages. There's not a clear place where to put it. And so I think the document is fine, this representation. I need some algorithm on top of it. Okay, so let me show you one possibility, which is not the actual pattern we're going to. This is called an iterator. How many of you have used iterators? Okay, how many of you have programmed iterators? A few still. So this is about, when you have a structure that is a collection, it may make sense to expose an API that separates the traversal from the actual action that gets done on each individual element. So when somebody writes an iterator, somebody programs an iterator for a data structure, they don't care what you're going to iterate, what you're going to do on each element. They just give you a way to see every element in turn. So, and this is how you use an iterator. You would create an iterator with some function, and then you'd have a method to initialize the iterator. I just picked an example from Java, but there's other designs. This gives you the first element. I.current gives you a reference to the first element of the iterator, right? So the current element of the iterator. I.next advances to the next element, and I.hasNext tells you if you're done, if it makes sense to call I.next. So many languages have iterators like this. Java has one that looks quite like this. Python has iterators. Ruby has iterators. They have simpler syntax. So in Python, when you build an iterator, it's very easy to actually use. You just use the for construct. For element in ... This constructs an iterator, and the for loop knows how to use the iterator to run some body, some piece of code for every element of the iterator. Okay? You've used this construct in Python, those of you who program Python, right? Ruby has something similar. I don't know Ruby, but it must have. Right? There's blocks, I think, called, or something? Okay. So this is a very common... So one solution that you might think of is you take your data structure and you program an iterator. Programming an iterator means writing code for hasNext, current, next iterator, and it would follow the structure, and it would allow you as a user to just say, let me see all the character glyphs in this, and it would iterate over the leaves, implementing, taking care of its own traversal. Okay, so that's solution number one. It's actually a pattern, but it's not the one I wanted to focus on. Do you have any questions about iterators for now?
Why is there the exclamation point for the I.hasNext?
Okay, because of a mistake. So that was meant to be a logical knot, but of course in a for loop, it has to be like this. Does this clarify? Okay, good. And thank you. Other questions or bug reports or anything like that? Okay. So that was a simple answer. Let's move on now to a little bit of a few comments about the iterator. So the iterator is actually a great thing, and you should have an iterator whenever you program a collection. If your collection is represented as a list or some built-in data structure in your language, you have the iterator. It's built in. The language library has it. But if it's a bigger data structure like this, you may have to program the iterator. So the iterator is very good when you need to do something simple on something uniform on all elements of the data structure. But probably for your document, you would need, how would you count pages? Well, you need a different iterator that goes over the pages. If you were to do something to all columns, you need an iterator for columns. So you'll probably end up writing several iterators, and you'll never know whether you have them all. You may, in fact, want to write an iterator over words. If you think that you'll need to traverse the word structure, you write an iterator that gives you every word in turn, and it takes care of all of the difficulty of finding words across pages. Is there a way to write, a more powerful traversal, more powerful than the iterator that can solve all of these issues all at once? And yes, and that's called the visitor. So the visitor pattern is a generalization of the iterator. And just like the iterator, it encapsulates the traversal of the internal data structure. It allows you, as the user of the visitor, to specify what to do on each element, but it gives you more control. It will, for example, the iterator for our document will allow you to do something for every page, something for every glyph, something for every column. Optional. It will be optional what you do for what element, but you'll get to see the entire structure of the document. So the idea, and this is going to be very abstract for now, but we have 2 slides of example. Whoever implements the visitor is going to implement the traversal of the whole tree. And it's going to call a doIt method for every element type, for every page, for every column, for every line, for every glyph, for every picture if you want. And you, as the user of the visitor, you get to implement what to do for every page, for every column, for every word, and so on. So let me show you some code first. Assuming somebody wrote the visitor for our document, how would you use that visitor? Let's say you want to find a particular character. So this is a search the entire document for all occurrences of the letter A. You're going to write something like this. You define a new class, which is a visitor. Let's ignore this knob visitor for now. You're going to define, or you're going to override the method visitCard. Essentially tell, I want to know about every character in this document. And this is going to be not just every glyph that's of type character. This is going to skip over images and drawings and such. So this is some sort of a filter. You tell, I'm only interested in characters, and C is the character that I'm visiting now. If C is A, then I'm going to print that I found A, and might even print the line number and such. Okay? And this is all you have to write to find the character A. This is how you'd write a counting line visitors. You initialize the counter to 0. This is done when this object, the visitor object, is instantiated. And then you write the visit line method, which increments the count. So this is going to be called on every line. Okay? So this is pretty cool. You didn't have to worry about even what's the data structure that represents all this. You just say, call me when you encounter the next line. I'm going to do something with it. In this case, I just counted. And this is the no-op visitor, which I kind of specified here as a superclass. This gives me the extent of what the visitor can do. So this visitor will be called on every character, every line, and every picture. And in fact, I could have had every column, every page, every drawing of various kinds. And it does nothing. It just returns. Okay? But I have it there as the prototypical visitor. This is a superclass of all visitors. And notice how I'm inheriting from visitors. So do you understand how to use visitors? How you're supposed to use them? No? So then ask me a question. Which part of it? For these examples.
What happens when you call visit car on like a picture?
That's, okay, very good. You don't call. It's the document that's going to call you. So this is a callback if you use these things. So you tell the document, call this function on every character in turn. And here you specify what you want to do on every character. But you're not in control anymore. This is essentially turning the iterator upside down. In the iterator model, you, the user of the iterator, are in control. You start the iterator, you tell it to advance to the next, you ask it what is the current element, and you do something with it. This is different. You put the control onto the document, you just specify what you want done at for everything that it encounters. And then it just calls you back. It does the traversal and calls this function. And this is going to get clearer in one slide. Other questions?
Wait, where do you write the code to detect what's the type of element that you're iterating?
That you don't write that. We're going to write that once in the traversal of the document. So just like the iterator, the visitor has two sides. One side is the library writer, the one who writes the traversal, and the other side is the user of the iterator. Okay? This is the user of the iterator part. The actual traversal is going to be done in separate code, which you don't have to even understand very much to use the iterators.
But so in the very first naive implementation, where we wanted to expand the entire tree and then like handle all the edge cases, even though it's harder to follow and code for, isn't it much more time efficient than this would be? Because like when you generalize it, like to just some visitor class.
No, it's going to be exactly the same operations. No, efficiency, because it's the same operations that you're doing. What do you have to do? You have to do the traversal. And then when you get to the parts of the document that are interesting to you, in this case lines, in this case characters, you do something special. I want to take that special thing out of the picture because that's going to vary between different traversals. And I want to keep the actual scanning of the document. That's the refactoring that I'm doing. I'll take more questions about this because it's not obvious. And I'll actually describe, I won't write the code for the scan. It ends up being some trivial code in the end, but it's more interesting to understand the flow of control between the different elements. So we have four actors in this example. There's a line that contains two characters, A and B. Each one of these glyphs implements a method called scan. This is a little bit like your spell check. Plays a similar role, except it's more general. It's any scan. Okay, so there's a scan method on the line, there's a scan method on the character, and on the page and the column section. And these scan methods are implemented once as a library. Separately, the visitor, this is a class that implements some specific methods that tell you what to do with each character, what to do with each line. This part only tells you to traverse the document. This tells you to do something to every element. Okay? So the visitor pattern separates these things. And control, as I said, the way this works is you create a visitor, this let's say to count lines or to find a character, and then you call the scan method on your document. And that's where the control is. The scan method, let's say in this case for a line, this, what I'm trying to show here is that I'm calling the scan method for line L, and I pass this visitor to the scan method. The line says, okay, I'm a line, and I'm being visited, I'm being scanned, so I should tell the visitor that a line is being visited. So the implementation of the scan method in the line calls v.visitLineL. This is how the visitor gets notified that there's a new line being visited. And it actually gets the line as a parameter. And it does something to it. Perhaps counts the number of lines. And then it returns. Well, then, now we have notified the visitor that the line has been encountered. We have to descend down to our children and visit them, scan them. So I will call the scan method on the character A, passing it the same visitor. The scan method for a character calls visitCar to the visitor. When that returns, I'm done visiting, and I call the scan method on the second character. Okay? So this part implements the recursive traversal. But put yourself in the shoes of the visitor. The visitor just sits there and gets notified for every line, for every character in that line, for every page, for everything. And it can decide to selectively do something on some of those operations. Any questions now? So now I expect you to be able to understand what visitors are. If you haven't, ask the question.
Visitor encapsulates different types of glyphs.
Okay, so
you have
this is the visitor. The visitor encapsulates the different operations that you want done on glyphs, on various kinds of glyphs. What you want done for every line, what you want done for every character. It doesn't know how to find the next character in the document. That's the scanner, which is implemented by the nodes, by the glyphs themselves. Other questions? How many of you would know how to write the scanner for our document structure? That means all? Yes.
Is this the same as like the iterating gradient method, and then you pass it to the function
Yes.
that as you iterate, you call the function?
Yes. So if you've used a map, for example, or a map operation, you pass it a function, and it will call this function for every element of a list, for example. Okay? It's very similar, except it's not for a list, it's not for a built-in structure, it's for your special document structure, for your data structure. And just like the map, it's separating the traversal from the actual action that happens. You specify the action, and then you get to reuse the traversal, which is the implementation of the map. Do you have any questions? If not, it means you're going to study this. This is going to be in the midterm. Okay? It means you're going to study this on your own. Okay. You're already... okay. Let's move on then. So, none of you raised a hand that you could write the scan, but this is what it is. It's a two-liner. Okay? For example, for every glyph that's really an internal node, what it has to do is to call the scanner of the children. Okay? When you get to the leaves are going to essentially just call the special method on the visitor to say, I'm a character, I'm a picture. So for a line, we have to both call the visit line, and then we have to call the superclass scanner to visit all of the components of the line, which in this case are going to be some of these characters or pictures. Okay? We move on. We don't have any questions. Any questions? Yes.
So I'm confused about two things. First, what is the V up there? Second, how is this different?
Okay, the V is, well, yes, this is missing from the slide. It should be like here. V should be it's the name of the actual visitor passed into scan. So you call scan, giving it a visitor object. And you pass this visitor object to the scan methods of your children. And they, in turn, will notify the visitor. This is different from the iterator in that it's a generalization of the iterator. The iterator could be seen like this, except it only has one. The iterator has only one function, one thing to do for all glyphs. This allows you to specify different things to do for characters, for pictures, and for lines.
Why is there a super scan?
Because I need to iterate over line being a composite. I need to iterate over each of these children. So super.scan calls the superclass scan, which is going to be this implementation. Yes.
So suppose I had an iterator and I just checked the type of whatever object was being returned from the iterator. Can I get the same functionality as this, or?
Yes, you could. You could write an iterator that makes, going back to this, makes the same sequence of calls. Okay. You would get the same functionality, but you'd be. So first, I mean, you'd have to. Let me go back a few slides. To the iterator. Okay. So you'd have to write this boilerplate every time, which now you don't have to write anymore, because this is incorporated in the scan method. And here, this would end up being a bit complicated because you'd have to check the type of current and see if it's a line, then do something. Some iterators are actually quite complex. They do something for every line, they do something for every character, and sometimes there's dependency between them. For example, what would be if you want to count how many words are hyphenated, you have to scan every line and every character in every line, and if it's the last character of a line and it's a hyphen, then you have to count. Okay, so imagine how you write this with an iterator. But it's doable. It's just a little bit messy. With an iterator, with a visitor, it allows you to kind of separate out the different traversals for the different types. Okay. Other questions? A few slides. Okay, so look again now, after you've seen the dynamic, the sequence diagram. When you write this code, you don't worry how somebody's going to find all the characters, and the scan method will worry about that. And it simply does it by traversal. You just tell it, I need to be notified for every character, and I'm doing something for every character. In this particular case, I'm looking for one. And this is another iterator. I'm using the same exact scan method. That's the beauty of this. You can do so many things, so many traversals, by writing the scanner once and then writing these very small iterators every time you need to iterate, to do something for everything in the document. Okay. That's really all it is. Okay? So this code is only written once and shared, and you just have to write a new instance of the iterator every time you want to do it. So this, the visitor pattern, you may need to customize it to your document, to your data structure needs. For example, one customization that I often have seen, the visit line being a composite, can return a Boolean which tells the scanner whether to bother to visit the children or not. Because if you want to write a counting line visitor, there's no point in visiting the line and then scanning all of the characters. And you do that by essentially returning from the visitor to the scanner some information that tells it how to continue the scan. Or sometimes you control the visitor for a line can control the order of the traversal of the children and so on. So this way the scanners and the visitors get a little bit more complicated. You get more functionality over it. So this was the last design pattern I wanted to describe. But I think you get the idea of how this works. There's a general problem, and then there's a recipe for a solution. The recipe may or may not apply to your concrete problem at hand, but whenever it applies, then you get the benefit of people having tried this before and seeing that they actually work and they generalize more than one problem. I will not test you on other design patterns, others than the ones we have seen in class. But these ones, at least, I would like you to know, to understand, and to know when to apply. If you go and look at what other patterns there are out there, and you should try to look to a catalog of patterns, you will find that there are classes of patterns, and there are some patterns that are small variations of each other. So, for example, the iterator and the visitor are very related. Perhaps some problems you can implement with one or the other. Typically, you wouldn't implement both an iterator and a visitor for the same data structure because the visitor can do everything an iterator can do and more. So probably use only one. Okay. In fact, this set of slides, which are online, contain more patterns, even here, but we're not going to be looking at that more. So at this point, we take a short break, and I'll put up the next puzzle today. Okay. You don't know how to find it, but it's there. Typically. So being able to get it out, it's really great. So this lecture really starts a new pattern of lectures. Okay. So this class, the lectures in this class were organized in a specific way. The first few were really trying to warm you up, and then came the warm up to go with that. Then we learned a little bit of what you need to even get your projects, the semester project study, requirements, how do you express requirements, extreme programming, use cases, how do you write up your designs, and that's when we did UML. How do you even put things together in the design, and we've done software architectures, all of you controller, and design patterns. But now, in fact, I believe you could go on with what I've taught you and do a reasonable job of software engineering on your projects. So while you're going on and doing this, I will switch gears and I will start teaching more advanced techniques that you may or may not use directly in your project. So at this point, the class is diverging a little bit from your project. And your project might be some game written on some platform, and you encounter day-to-day some difficulties using some libraries, language, REPO, and such. That's not what the rest of the class is going to be about. I'm going to start teaching technologies and tools, and I hope that many of these will be generally useful in this project, but if not, in your next project, in actual real job. So today we do version control, and again, I believe all of you will use version control, but perhaps some of the advanced techniques that we teach here won't really come up. Then we'll have a bunch of classes on testing, actually maybe 5 or 6 classes, because there's a lot to do there. And I expect we will do some testing, but perhaps not everything that we'll be teaching on here. And then we go to more advanced techniques. I wrote here formal methods, language support, but I'm actually now thinking of adding security, writing secure code, and I want to have a unit on deployment. Even though this is not something, I mean, Heroku did the deployment for you. You just run some commands. They worry about how the servers are going to be up and how they're going to be talking to each other. But it's actually an extremely cool thing that you will need to face when you write real code. Okay, so that's really how this fits. So I'm going to spend very little trying to argue why you should use version control, because I expect you're already convinced. And then a little bit about basic operations, which I expect you know. Then getting into a little bit more advanced things, like branches and when to use them, merging, which is the inverse of branching, and what could go wrong and how to get back from that. Distributed version control, which Git is a version of it, but how do you really use it in a distributed team? Throughout, sprinkle some good practices, lessons learned by me and others about how to organize this whole work. So keep in mind, Git and other version control systems, they're just tools. How you use them, it's a separate thing. And you could use Git badly, or you could use it well. And unfortunately, it's not easy to switch. If the organization has started using Git in a certain way, it may lead to a lot of trouble. In addition to just lecture, I have prepared a demo, which we'll be doing here next lecture in class, just like following the model of the simple web app demo, where we programmed the first web app, or what other demo did we do? No, this I guess is the second. And we're going to have another one about testing. Okay, so next lecture, bring your laptops, and we'll be actually trying to use it ourselves. So let me start with a very simple use case. You're a single developer, okay? And even a single file, you should still use version control. You have your file, let's say, in a local copy, and over time, you make changes to that file. So let me ask you, and then occasionally you decide that this is a good version, that I'm going to do something with it. I'm going to release, I'm going to give it to the testing team or whatever. Why would you still use version control if you are the only one, and it's so simple as a single file? Okay, so I missed the first thing you said. Oh yeah, so if you lose stuff, okay, you could use a backup for that.
Say someone's using an old release and you need to look at the code from that particular version.
Right, you need to find out how things look back in history. Good. Other reasons. You're using Git. Why?
So that one person's mistake doesn't break like the description of everyone.
Such that one person's mistake does not affect the others. But here you're a single developer. It helps with that, but not in this case.
Being able to log when and description for what you did on a certain day.
Right. Yes. Finding out. I mean, sometimes you look at the code and say, "Why is this conditional here? This doesn't make sense." Either somebody made a mistake or they put it in for some reason that's not obvious. You can look to the history, find out when it was introduced, what comments were made around that check-in. It's very useful. Okay. So let's see. What do I have here in the slide? You can revert to an older version, and you do that sometimes to discard recent changes. So sometimes I embark on this kind of exploratory path, and I know it may go nowhere, so I commit. I save a snapshot, which allows me very easily to throw away everything and come back to the state. But sometimes you want to test when a bug was introduced. I have a bug, and I knew for sure that this bug didn't exist a month ago. Sometimes it was introduced. Being able to restore the project with various stages and test for the bug, it's very helpful. We'll learn a whole technique, delta debugging, that works around that idea. Compare current version with older, see what has changed recently, and this is the git blame part. Find out when a certain line was edited and why. So what we see, version control, sometimes also called source control management, or SCM, what it does, it tracks the history of your project. Okay? So it tracks the multiple versions. And this could be different releases, but maybe you could save your releases as tarballs in a special directive. Okay? So that's how people used to do it before using version control. But with version control, you can do this a lot more often. Different versions of the same release. Conviva is now, after 7 years, at I think we're 90,000 commits. So we have history of 90,000 commits. Some of them small, some of them big. We have them all. There have been version control systems that have saved every single time your text editor has saved the file to the disk. Okay, but that's probably an extreme. It's not something that's not how you use Git. What are the basic operations that you do? First, so I'm going to be introducing some definitions here, and these are following common terminology. So the repository is typically a database, but you can think of it as being many snapshots of all of the files in your project, except it's represented as very compactly as a database. And in it, one entry is a commit. Okay, a commit is a snapshot of all of your files in the project. You don't edit the repository directly. In fact, if you've looked at Git's repository, you can't even comprehend where things are and how they're represented. It's all a big, I wouldn't say a mess, but it's a complex data structure. What you do is you check out, meaning you take a snapshot out and you expand it in your file system, each file in its own place. And that operation is called a checkout. And when you do that on a local copy, okay? So we have to keep in mind for the rest of this set of slides, we have the repository and what's in it. It's a database. And the local copy is a snapshot. It's your file system, where you're working, where you're doing the edits. So this is every time, perhaps, you have made an edit on your local copy. And occasionally, you take your snapshot of local copy and add it to the repository, add it to the database. Okay? So this database here, it's additive for the most part. And that's what I said earlier on, that when somebody says that I've lost my work, it's probably not true, because in Git, for example, very rarely do you delete from the database. You keep adding. So if you had something in there before, there's typically a way to get it out. Might not be obvious. How? Okay. So each of these blobs, these snapshots, is called a commit. Or in Subversion world, it's called a revision. So it's a snapshot of your files, but there's more to it. There is the date when it was made. There's the author, and the comment that the author got to make when they saved them. For the purpose of the database, these are identified in various ways. For Git, these are hash values. And it's really a very powerful concept that it's worth understanding. Imagine that you take the snapshot, which is the entire file system, and you hash it all of its contents gets hashed, which means that if every bit in it is changed, this identifier changes. Furthermore, you hash not just the contents of the database, but also its parents, its history. Okay? So the same snapshot of the file system today, as opposed to a year from now, when maybe you've added things and then deleted things, you got to the same state. It's going to have different hash numbers because it's a different thing. It has a different history, even though the content might be the same. We're going to elaborate on that. Why is that very important for something like Git, but it's not important for Subversion? It's because Git can be used in the distributed way. If you don't understand exactly what I'm saying, it's going to come in the next lecture. Any questions so far? I assume this is all boring. Moving on then. I'll give you time to fall asleep. So the local copy is not just a simple set of files. It also keeps track of how it relates to the repository. So typically it knows to what revision in the repository it corresponds, and the time of the last commit. And based on this, the version control system can classify every file in your local copy into 4 categories. Most files will be unchanged and current. Unchanged means that you have not edited this file since the last time you checked it out of the database. And current means nobody has committed to the repository a change to this file after you checked it out. Okay? So keep in mind, you check out, you have your files. The people may be committing to the repository, maybe making changes to this file. It's not going to show immediately in your local copy. But the version control system knows whether the file has changed. Most files are like this. Okay? To give you again an example from Conviva, our repository is 2 gigabytes. We have 2 gigabytes of essentially stuff that's checked in. Every single day, we edit a small number of files, a small number of lines. So most files are in this category. I've checked them out, and nobody has touched them in the repository. So they are current. If you were to do a checkout again now, this file wouldn't change because it's a current. If you were to commit, nothing would need to be committed because the file is unchanged since the last time you checked out. Okay, that's most files. These are the files that you've changed. You've checked them out. You've made changes to them, so locally changed. They are current in the sense that nobody has made changes in the repository to the same file. So you're probably the only one editing them. If you were to do a checkout now, well, this is actually different. If you were to do a checkout in Git, it would override your changes. The checkout in Git means no matter what, give me the copy from the database, from the repository. In Subversion, it's a little bit different. You will not lose your changes. Okay. Unchanged but outdated. This is a file you checked out. You haven't edited, but somebody has committed a new version. So if you were to check out, you're going to get the new version. And then there's one more. What's the 4th combination that I'm missing? Just wake up check. Somebody else? I guess it's only people in the front that can see that far. Maybe the font is too small? No? Locally changed and outdated. This means you've checked it out, you've made changes, somebody else has made changes. This is where the action is going to be because you have to figure out what went on with this file. Too many people are editing this file. Okay. You can see the history of commits. Git log does it for Git. SVN log does it for Subversion. And if you just do it out of the box without any parameters, you see these nice names, which I told you are hash numbers, the author, the date when it was made, and the comment that they wrote up. And I assume you've seen all of this stuff before. We're going to talk briefly later about what makes sense to put in these commits. How do you even, what kind of structure makes sense to have in the commits. But Git will accept anything. Okay, let's now move on to a more complex scenario. This was just to introduce the actors here. And the next complication is branches. So far, the repository keeps the history and allows you to go back in history, compare with history and all that. But let's say that at version 13, this snapshot you released. You put on your production servers and people are using it. But you haven't stopped developing, so you keep making changes to it. And then somebody discovers a bug in this production version. A bug that you have to fix in here. And maybe hotfix. Hotfix typically means something that gets released out of the normal schedule, typically a patch on the production servers. It has to be fairly quick. We can't wait until the next scheduled release. So what we do, and this is one thing that the version control system can do, is to say, create a branch at version 13, bring version 13 on my local copy, and I'm going to make a change, and I'm going to commit it. Now, when I commit the local changes from my local copy, I cannot put the commit here in 16, because this 16 is based on 13, some changes on top of 13. So this immediately creates a branch. The database structure is going to look something like this. In Subversion, you have to really issue some special commands to create this branch. In Git, it will happen automatically, simply by checking out something that's not the latest version, making change in it, and committing, you're going to create a branch. Okay, so branches are very easy. People say branches are cheap in Git. The truth is they are equally cheap in Subversion. It just takes a few more keystrokes to create it. Okay? So now we're going to be able to allow the developers to continue on their development, but we also have this version 16, which is a patched up version of 13. So to give you an example, back again to Conviva, we have about 100 branches now, and about 5 or 6 of them are in active development. One of them is we call it trunk, where people actually make changes day to day. One of them is the version that's being tested, and our testing team finds bug. Developers called in to make a fix in that version. And a couple are in production in various stages, various versions, various customers. Sometimes even those need hot fixing as well. And so somebody in your organization will have to not just know how to use Git, but design the structure. We're going to talk later, next lecture, about how you use branches. But for now, let's focus on the mechanics of what a branch is and how you can use it. Okay. So what do you think are other uses of branches other than making hot fixes on releases?
To develop a new feature and possibly break stuff, so you don't want to disturb whatever.
Okay, so you create a branch to isolate the changes you are going to make from the rest of the team. Good, we call those feature branches. Other uses of branches.
When you want to optimize, and then you have like the system and multiple large systems and small systems, and then you want to optimize separately for those two.
You want to write separate optimizations for different scenarios?
So, like when you're processing like a few hundred megabytes, you want it optimized differently, and when you're processing like several bytes.
True, you may need different optimization for different scenarios, but I would not use a branch for this. A branch means essentially it's duplicating your code, right? So you would like to have one code base with all optimizations that kick in at different stages. So maybe I didn't understand the exact scenario that you're pointing out. Other branches, other reasons for branches. we also use branches to snapshot the code essentially for testing, as I just mentioned before. We keep developing all on one branch called trunk. When we're ready for the testing team to start testing something, we can't ask them to test something that keeps moving every minute. Okay? We take a snapshot, we pick a particular revision, and say, this is the revision that you should be testing. So they test that, and they don't care. They don't want to see all of the new features we're adding in. Okay? So they test a particular revision. In the ideal world, that has no bug and gets released, but it's never like this. They find a bug in this version. Now they call in a developer to make a fix. Okay? So the developer has to then create a branch and make a fix on this particular branch, because the testing team wants only the minimal number of changes on top of this kind of frozen code base. So we use branches for that too. Okay, so that was snapshot of code testing, private versions, the feature branches, but all of these eventually want to merge back to trunk. You don't want to be an organization that has to have this long-term memory of multiple code bases. It's very, very disruptive. If you're you're a firm like Microsoft, you have to, okay, because you still have to maintain Windows 7. Windows XP just stopped being maintained, so they're probably closing up that branch of the code. And Vista and all that, and you have to assume those code bases are so different that they are probably different branches, maybe even different version control systems, different servers altogether. Okay, so what we're going to be doing next is the mechanics of working with branches, especially merging and what to do when merging goes bad. Let me stop here. So also next time, depending on how the timing works, I'm going to sit down and do a demo of some more advanced Git features. More advanced than I assume you normally use, but very useful nevertheless. Thank you.
I'm sure